Welcome back, everyone. Now we have Ian Roque from Cambridge University, who will talk about advanced Bayesian calibration pipeline for global 21 centimeter experiments. Ian, can you please share your slides?
Okay. Hi, I'm Ian, and I'll be talking to you about advanced Bayesian calibration for global 21 centimeter experiments. We are, of course, looking for the cosmic 21 centimeter signature, which would provide observations of the dark ages, cosmic dawn, and the epoch of reionization. These will in turn reveal the formation of cosmic structure as primordial gas interacts with the first luminous sources. It's called 21 centimeter astrophysics because we are observing the hyperfine transition of neutral hydrogen, which releases a rest frame photon with a wavelength of 21 centimeters, redshifted into the radio wavelengths. There are two methods of detection for the 21 centimeter cosmic signature, the first of which is the measurement of the 21 centimeter power spectrum. This would provide observations of individual sources. On the bottom here, we can see an experiment that uses this method of detection. On the left is HERA, and next to it is a simulation using 21 centimeter fast of what a potential observation using this method of detection would look like, in which we have pockets of primordial gas being radiated by the first luminous sources. Another method of detection is the global or sky averaged measurements, which would provide a bulk measurement of the ionization history of this cosmic hydrogen. And on the bottom right, we see an experiment that uses this method, which is EDGES. And next to it is the absorption profile seen by EDGES in 2018. Sticking with global experiments, this kind of experiment probes the energy ejection into the intergalactic medium, but it does not resolve the spatial features on the sky. These kind of experiments have a lower sensitivity requirement than the power spectral measurements and are conducted usually with single antennas. The smoother signal using this method, however, makes foreground mitigation challenging. On the right, we see a plot, and in gray, we see the signal range for an epoch of reionization cosmic signature, shown in gray again. And on the low frequencies, we see that this is dominated by galactic synchrotron radiation, plotted in green here. I mentioned EDGES before, and another global experiment that uses this kind of technique is SARAS, which is shown on the bottom right. My research in particular is with REACH, the radio experiment for the analysis of cosmic hydrogen, which is a global experiment that intends to advance the field with features such as an ultra-wideband system, the joint fit of systematic and foreground models using Bayesian statistics, the identification of unaccounted for systematics through maximally smooth functions, and the building of redundancy through simultaneous observations using two antennas, shown here on the bottom. On the left is the hexagonal dipole, on the right is the conical log spiral. REACH will be deployed later this year in the Karoo of South Africa, near the HERA site. One bottleneck for global 21 centimeter experimentation is calibration of the instrument itself. REACH intends to use a Dickey switching method with 12 proposed calibration sources that have been strategically chosen to sample noise waves better than the standard open and shorted cables used in other experiments. On the right here in the middle, we see a Smith chart with 4 of our calibration sources and a simulation of one of our antennas shown in pink. Our goal is to choose these calibration sources to sample as much as this Smith chart as possible and gain as much information on the instrument as possible. In our calibration process, we will be deriving calibration parameters that correct for the antenna mismatch and response. And our goal is to make this fully autonomous to allow for simultaneous calibration and observation in the field. On the far right, we see the current state of our receiver. As you can see, it's not complete yet. We don't have RF shielding, temperature control, etc. But how exactly does our calibration procedure work? It is based on the EDGES procedure, in which measurements of the power spectral density, reflection coefficient, and temperature at the receiver input shown here in would be related to a final calibrated temperature shown here in blue, a box in blue in this equation, through the derivation of noise wave parameters shown in red that would describe the noise properties of the instrument. And these noise wave parameters would be solved for as frequency-dependent polynomials. Taking a closer look at the equation, we see that each block isn't squared or to a higher order term. It's a linear calibration equation. And so through an assignment of notation, we can gather all of our measurements into an X matrix shown on the third line on the left, and all of our noise wave parameters, our calibration parameters, into our model theta shown on the third line on the right. Using this notation, we can condense our calibration equation to this bottom equation, which is solved for using a linear regression model, tcal being our calibrated temperature, x being our measurement, theta being our model, and sigma being our noise term. In derivation of our noise wave parameters, our model theta, we assume a multivariate normal distribution for sigma. We specify conjugate priors to solve for the posterior distribution of our noise wave parameters without having to integrate. We also use evidence comparison to determine individual noise wave parameter characteristics that are favored by the data. On the top right, we see our prior distribution, which leads to our posterior distribution through an updating of the distribution hyperparameters showed in the last four equations on this slide. What are the benefits of using this kind of conjugate prior approach? Well, using the conjugate priors allows us to avoid multidimensional integration, which leads to an algorithm that's much faster than, say, a Monte Carlo approach that explores the entire multidimensional parameter space. This speed allows us to calibrate in the field. Another feature of our pipeline is the joint solution of noise wave parameters that incorporates possible correlations between these parameters in the derivation. On the far right, we see the posterior distributions for two noise wave parameters, TNS and TL. This gray sliver, horizontal sliver, are the posterior distributions from our calibration pipeline using only information from a single ambient temperature load. In red, we see the posterior distribution from our pipeline using information from a single heated load. As you can see from the skew of the red posterior, there's quite a bit of correlation between TL and TNS in this example. And as one would expect, the posterior distribution from using the ambient temperature load and the heated load in tandem is found in the intersection of these previous two posteriors, which is shown in blue in this zoomed in portion of this plot. Finally, another feature of our pipeline is the individual optimization of noise wave parameters, which prevents potential information loss through fitting out any cosmic signal by assigning maybe a blanket polynomial order, which has been done in previous experiments. Here are the results of our pipeline using simulated data. These simulations are based on empirical measurements of the reflection coefficient, in which noise wave parameters, which we have specified, along with our simulated reflection coefficients and our equations, are used to build mock power spectral data, which are submitted to the pipeline. And we verify that the returned noise wave parameter distributions match those of the user-specified noise wave parameters. In these plots on the right, the user-defined noise wave parameters are shown in red, and in black, we see 1,000 posterior samples from our pipeline. The bottom right shows our calibration solution applied to an ambient temperature load at 298 Kelvin, and our calibration solution achieves an 8 millikelvin RMS error from that measured temperature. During the building of our reach receiver, we have tested this pipeline on a Hera front-end module using 4 calibrators and using a noise filter as an antenna. The measured temperature of the antenna is 304 Kelvin, and our calibration pipeline achieves a solution with an RMS error of 236 millikelvin from the measured temperature, which approaches the expected limit for a Hera front-end module using this kind of calibration based on the kind of components used in this instrument and the gain blocks in there as well. Now, there is some structure to be seen on the right in our calibration solution, but this structure is within air, so I hesitate to overinterpret this chromaticity as of now, especially considering our next plot, which is our results on the partially built reach receiver. Again, we are using the noise filter as an antenna, and 12 calibrators are used, and we take 2-minute integrations on the power spectral densities of these calibrators, and with our measured antenna temperature of order 302.8 Kelvin, our calibration solution provides an accuracy to within 1.075 Kelvin RMSE. Again, we've taken only 2-minute integrations. So by extending our integrations to 24 hours, we anticipate that this RMSE can reduce to 30 millikelvin, which is comparable to the calibration accuracy reported by the EDGES experiment for a low foreground sky. And so our future work is primarily finishing the development of the receiver and primarily testing our algorithm with longer integration times, as well as improving our the accuracy of our temperature measurement. RF shielding, temperature control, and automation are also primary features of our calibration procedure that we'd like to implement, as well as improving our model comparison for more accurate noise wave parameter derivation. Finally, we plan to deploy this instrument in the Karoo of South Africa later during the summer, and hopefully we can test this out and bring you real data from a 21 centimeter cosmological signal. Thank you.
Thank you, Ian. Do we have any questions for Ian? Please post them in the Slack or Q&A. Okay, so there is a question on chat. Smoother signal makes foreground mitigation challenging. Can you elaborate on that?
Let's see. So on the bottom, we have a simulation of the 21 centimeter signal from a hearer perspective using a power spectrum measurement. And we see these individual pockets of these primordial gas clouds being radiated. And these are very rigid bubbles that show the primordial gas being radiated to the extent of the radiation, whereas the kind of global sky average measurement is just an average over the sky. So you just get this brightness temperature, this absorption trough, which is on the order of about 200 millikelvin difference from the cosmic background. And of course, looking at this further foreground plot, we see that the synchrotron radiation is many orders of magnitude, maybe up to 5 orders of magnitude higher than this 200 millikelvin deviation from the cosmic background that we expect to see from this very smooth global signal.
Thanks. Rahul has a question. Can you unmute yourself and ask?
Yeah, can you hear me?
Yep.
Thank you very much, Ian. A very nice talk.
Thanks.
My question is, do you have requirements for your S11 accuracy, and are you meeting them at the moment during calibration?
Well, as you've seen, we are still testing the calibration procedure on a partially built reach receiver, which, as we saw in a separate picture, doesn't even have RF shielding yet, temperature control, and accurate temperature measurement. As of right now, we are measuring to, I think, within 5 dBs, our S11. So as of right now, with our anticipated calibration accuracy, I believe we're meeting our S11 requirements. But once the receiver for reach is built, we will have to explore exactly how accurate we need to make these S11 measurements.
Thank you very much.
Mm-hmm.
Let's thank Ian again and move any question and answers to the Slack. So the next speaker is Hyoyin from Kapteyn Institute. She'll talk about comparison of direction dependent calibration performance of DDE-cal and SAGE-cal in LOFAR UR context. Please go ahead, Hyoyin.
Okay, do you hear me well? Do you hear me?
Yes.
Okay. Thank you for the introduction, and thanks for the opportunity to present our work. So I will just start right away. So as we have already discussed a lot yesterday and today, there are many challenges when you want to detect the EOR signal. And mainly the observed data contains not only the EOR signal that we would like to detect, it also suffers a lot from astrophysical foregrounds, which are 3 to 4 orders of magnitude higher than the signal. But also there are effects from ionosphere, instrument, alpha, as well as all the other effects. So it is important to understand those effects and calibrate them precisely. So over the years, LOFAR EOR team has been working on developing the pipeline for processing the data and also calibrating the data. So there are many steps in our pipeline, starting from pre-processing, including some alpha flagging, etc. However, in this work, we would like to focus on the direction-dependent calibration part of the pipeline. And the main goal of the direction-dependent calibration in our pipeline is to use a sky model to predict visibilities and subtract them from the data. So these are the main setup for the experiments that we are doing in this work. So basically there are two important points. So mainly we are using two different direction-dependent calibration algorithms, DD-cal and SAGE-cal. So we have been using SAGE-cal for doing the direction-dependent calibration for our data. So it has been working pretty well. However, we have never tried other methods. So here we would like to use another method, which is DD-cal, also developed for calibrating the data for LOFAR, to see whether these two independent direction-dependent calibration algorithms produce similar results. So there are some differences in their setup. So for example, DD-cal uses a model with intrinsic fluxes, while SAGE-cal uses apparent fluxes. And for DD-cal, we also use a beam model. And for SAGE-cal, we do not use a beam model. However, we are using the same sky model with the same number of clusters and components. So if we see any difference in their performance, it's not because of the difference in the sky model. And we also include CASE and Cygnus A model into the model, because even if they are really far away from our field of view, they're so bright, they still enter the field of view via side lobes. So we need to also correct for those two sources. We actually use slightly different models for DD-cal and SAGE-cal here, mainly because those two methods, they have been developed for different purposes. And we know that these two models, they work pretty well for two methods. So we are using different models. And this is basically the setup for the direction-dependent calibration. And on top of that, for the strategy of subtracting CASE and Cygnus A, we have two different approaches here. So because they are very bright sources, so sometimes having them kind of entering through side lobes, which means when you are correcting or you are estimating your gains, they have influence on overall sources in the sky model. So if you subtract CASE and Cygnus A in a separate step, sometimes it helps improve your performance of the direction-dependent calibration. So depending on whether CASE and Cygnus A are subtracted in a separate step or not, so with the sky model, we have one-step and two-step approaches here. So they are basically the main setup for our experiments. So here we have two different calibration algorithms and two different approaches for subtracting Kasey and Cygnus A. And that means in total, we have 4 cases to study. And now I'm going to show the results. So first of all, we will show some images before and after direction-dependent calibration. And on the left side, we have the image after direction-independent calibration, which we only corrected for the flux. So we have a lot of components in the field of view. And on the right side, we have the results after we have subtracted the sky model. And as you can see, there's still some residual. However, a lot of sources are removed, and there are some differences depending on which strategy you use here. So we are, however, they are very similar. So now we are going to take a closer look at them and what are differences between their performance. So first of all, we look at the 2D power spectra after direction-dependent calibration with the 4 different cases that we have mentioned at the beginning. And overall, what's kind of encouraging is that these different methods, they produce more or less comparable power spectra. However, there are some differences. So first of all, we would like to compare the performance between the one-step and two-step method with DD-Cal. And on the right side, we have the ratio between this one-step and two-step method with DD-Cal. And you can see in each power spectrum result, there are 3 dashed lines there. And then from top to bottom, they are indicating the horizon, so 90-degree delay lines from the phase center and 20 degrees. And on the bottom, it's the 5-degree delay line, which is actually corresponding to the primary beam region. So here what we see is that the main difference between the one-step and two-step method is around the 20-degree and 90-degree region here. So it means that actually when Kasey and Cygnus A, they are subtracted in a separate step with DD-Cal, it shows better performance. So this is what we learned. And we go on and we again compare the performance between one-step method and two-step method with SAGE-Cal. And here, actually, we do not see that dramatic difference as we have seen with DD-Cal. So we see that there's a blue and red colors alternating, but then overall, on average, there's no huge difference between them. And the difference is very small for SAGE-Cal. And now we would like to compare the performance between DD-Cal and SAGE-Cal. So when everything is subtracted in just one go, including Kasey and Cygnus A, so we see still this difference. So there are 2 main differences. So one is from Kasey and Cygnus A, so between these 20-degree and 90-degree delay lines. So SAGE-Cal apparently shows better performance. And in the primary beam region, actually DD-Cal does a better job. And we think this is because for subtracting the sources in the primary beam, for DD-Cal, we are using a beam model. So actually it helps improve the results in the primary beam region. And now we move on to the two-step method. So if we compare DD-Cal and SAGE-Cal, here we only see the difference in the primary beam region because we have seen it already that for DD-Cal, it is better to subtract Kasey and Cygnus A in a separate step. So SAGE-Cal used to perform better at subtracting Kasey and Cygnus A. However, this advantage disappears when it's done in 2 steps. So we only see the difference in the primary beam region, and DD-Cal is better at subtracting sources in the primary beam region. And finally, here, after the direction-dependent calibration, we apply the foreground removal technique, which is done by GPR in our case. And they are on the bottom panel for 4 different cases. And what we can see here is that the residue in the wedge, they are well removed after we have applied GPR. So this means that, thank you. So this means that DD-Cal's advantage in the primary beam region basically disappears. So probably people were wondering, when you see this excess power between 20 to 90 degree regions, you might wonder probably they can also come from other sources. So to actually prove that they are from Kasei and Cygnus A, we created very wide images where we can also see Kasei and Cygnus A. And we exactly see what we have expected from 2D power spectra. So on the top panel, we have the results from DD-Cal, and from left to right, you can obviously see that Kasei and Cygnus A has reduced power if it's subtracted in 2 steps on the right side. However, this is not so important for SAGE-Cal. So on the bottom panel, you don't see that much difference between the 2. So finally, here we also calculate the two sigma upper limits of the 21 centimeter signal. So in the end, the 4 cases we have studied, they produce more or less similar results. However, SAGE-Cal with the 2-step method, it gives the better upper limits compared to others. So these are the things that we have found by comparing 2 different algorithms. And I'm going to leave you with the summary, and thank you for your attention.
Thanks, Hyoyin. Do we have any questions? If not, I have one small question. What is the difference between DD-Cal and SAGE-Cal?
So basically those 2 methods, they are designed to solve this radio interferometric measurement equation. So, so the way they optimize the solutions will be different. And also one of the major difference is how they do kind of frequency smoothing. So for DD-Cal, it kind of uses this Gaussian function to smooth the gains over frequency. However, for SAGE-Cal, it's not the same process. So it uses some function to penalize those gains which are deviating from their values. So yeah, that's the major difference.
Thank you. So let's thank Hyoyin again. And our next speaker is Ian Hendricksen from McGill University, who will talk about prototyping for the Canadian Hydrogen Observatory and radio transient detector. Go ahead, please.
Can everyone hear me okay?
Yes.
Okay. So hi, thanks for that introduction, and thanks to everyone for having me here today. So I'm Ian Hendricksen. I'm a master's student at McGill University Department of Physics. And today I'm speaking on behalf of the D3A collaboration to talk about prototyping for the Canadian Hydrogen Observatory and Radio Transient Detector, or CORD, with the Deep Dish Development Array. So CORD is a next generation radio telescope slated to observe over the next decade. It will consist of a core of 512 6-meter dishes at the DRAO. So this is the current site of the CHIME experiment, as well as 2 outrigger sites, which will be equipped with 64 6-meter dishes and a single chime-like cylinder. Cord will observe over 300 and 1500 megahertz bandwidth, which corresponds to a redshift of 0 to 3.7. The key focus of Cord is to make improvements on redundancy and systematic control. So in order to achieve this, we have several driving technologies, including precision surface dishes, a wideband feed, low noise temperature amplifiers, and a high data rate signal processing pipeline. So compared to Chime, Cord will have 3 times the bandwidth, twice the collecting area, and root 2 lower noise. But keeping these things in mind, some of the things that Cord is going to try to do are to make improvements in intensity mapping out to redshift to 3.7, as well as the detection of 10 to the 7 individual galaxies below a redshift of 0.4. Cord will also make tighter constraints on the dark energy equation of state parameters, as well as increased detection rate of fast radio bursts, and even make some probes of fundamental physics. So to achieve this, we've developed what is called the D3A, or the Deep Dish Development Array, which is the pathfinder for Cord technologies. And currently we have 2 3-meter dishes and 1 6-meter dish at the DRAO. Again, this is the current state of Chime. I'm going to be focusing on the 6-meter dish today, which I'll refer to sometimes as D3A6, so D3A 6-meter version, which observes across a 400 to 1600 megahertz bandwidth. We have 2 more 6-meter dishes planned for installation in the coming months, and we're currently conducting daily observations. So on the top right is a little figure of the 3-meter dish at the DRAO, and pointing out the 3-meter dish feed, which I should just mention that is not the same as the feed on the 6-meter dish, which I will be discussing today. And on the bottom is the 6-meter dish at the DRAO. So D3A6, or the 6-meter version of the Deep Dish Development Array, has prototyping focuses on the dish, the feed, the LNA, and the digital backend. So as I mentioned before, with Cord, redundancy and systematic control are absolutely crucial to the experiment. So we have a couple of design goals in mind, one of which is to keep the RMS of the dish deviation compared to a perfect parabola to be sub-millimeter. We'd like the feed to be wideband. The LNA needs to have a low noise temperature, and the digital backend needs to be capable of correlating the full bandwidth, as well as with sufficient spectral resolution. So on the top right here is the 6-meter dish covered by the radome, which is intended to keep snow off during the winter months. And on the bottom is the 6-meter dish, again, without the radome. So the first of the technologies for D3A6 that I'd like to talk about are the composite dishes, which are designed to be inexpensive as well as scalable to a large number of elements. And this is achieved through its monolithic construction design. So by this, I essentially am saying that the dish itself is poured over a mold, which both helps to keep the dish RMS errors sub-millimeter, as well as to keep the design cost down. The dishes are a deep dish design, hence the name Deep Dish Development Array, with an F/D ratio of 0.25, which is intended to reduce crosstalk and spillover. And like I said before, the dish RMS errors are intended to, and we have shown that they are sub-millimeter compared with the perfect parabola. So the 6-meter dish on the mold is shown on the top right, where the structural support ring is being mounted. And on the bottom is lifting the 6-meter dish from the mold. And you can see that it's a single cohesive unit, the monolithic construction design, not stitching together separate pieces to form a whole, but rather just making it one cohesive unit at the start. So these are laser tracker measurements of the first and second dish, as well as the mold. And in all cases, you can already see right away that the RMS is sub-millimeter. And I should mention that the mold is the primary thing that is contributing to the error. So if we can hopefully achieve a mold that is lower RMS, we should also hope to see this on the dishes. But the mold RMS is around 0.552 millimeters. And the first dish unpainted, it has an RMS of around 0.611 millimeters. So not too much of an increase in the RMS. And the key thing to point out here is that the first and second dish unpainted both have sub-millimeter RMS values, as well as they're pretty comparable too, at the around 0.6 millimeter level. So again, we're able to achieve both the redundancy, keeping them both consistent with each other, as well as systematic control, achieving RMS that is sub-millimeter. So moving on to the feed, which is a Vivaldi type style feed. It's dual polarization, and it is low cost and laser cut for repeatability. Again, hammering on the redundancy and systematic control aspect of the experiment. And on the right here is the reflection coefficient across the chord bandwidth. Again, that's 300 to 1500 megahertz. And what we find is that the reflection coefficient is less than or around minus 10 dB, which means that there's minimal reflections, there's low loss across the bandwidth, which is very difficult to do across such a 5:1 bandwidth ratio that chord operates over. And you can see that there are some resonances here as well that go to very low reflection coefficients. But the important thing to keep in mind here is that we can maintain this less than or around minus 10 dB reflection coefficient across the entire bandwidth. And complementing this is the aperture efficiency of the feed. So the aperture efficiency is the ratio of the effective aperture to the physical aperture. Things that could decrease the effective aperture include like spillover, things from the ground, etc., or imprecise reflector. And it's very difficult to maintain a high aperture efficiency across such a wide bandwidth. So there might be some instances where you may have seen aperture efficiency is higher than 50%, but across a narrower bandwidth, it's easier to match the impedance to achieve that sort of aperture efficiency. So the fact that we can keep it at greater than or around 50% across such a wide bandwidth is really difficult to do, and it's a good result. The next thing I want to talk about is the LNA, which is absolutely crucial to the signal processing pipeline because the system temperature is dominated by the LNA. So in order to have a more sensitive instrument to achieve that √2 lower noise compared to chime, the LNA has to be very low temperature. And what we find is that the LNA is nominally 10 to 20 Kelvin noise temperature. So if we look at the bottom plot here, this is comparing the minimum noise temperature, Tn min, to the matched noise temperature, Tn. So the minimum noise temperature is the smallest noise temperature that could theoretically be achieved with the LNA. So it's kind of like thinking of the LNA on its own, whereas the matched noise temperature takes into effect the impedance of the feed. So there's currently efforts to try to drive the blue line closer to the orange line, which would be the ideal minimum noise temperature that we could achieve. But even so, we're still already achieving 10 to 20 Kelvin noise temperature, which is already quite low. Another thing that's really cool to see about the LNA is that the gain is remarkably flat across the entire bandwidth, which is another thing that's extremely difficult to do, where often you might see a roll-off from an LNA at some frequency, but maintaining this flat gain across the bandwidth is really, really cool to see, as well as the fact that it's greater than 30 dB. So on the signal processing aspect of the experiment, we currently have commercial analog components that apply filtering and amplification that feed a modified chime ADC mezzanine, which then feeds an ICE board. So for those of you who may be unfamiliar with the ICE system, ICE is essentially the so-called F engine of other experiments. So chime is a great example where the F engine and the ICE system are the things that perform the digitization, channelization, and the corner turn operation before being sent to the X engine for correlation, to compute the correlation. But with this small number of inputs that we have, we can actually just compute the correlation on the FPGA itself. So the ICE board is essentially our digital signal processing backend. So there's two avenues for the chord backend, which we will try to prototype with D386. One is this current modified chime ADC that we have, where the ADC and FPGA are on separate boards. This is a reliable and demonstrated system, but because of the fact that the ADC and FPGA are separate, that means that we have separate boards between the ADC and ICE board. There's more cables that need to be involved because of the it's about 800 megasamples per second sampling rate of the ADC, which means that for chord, we'd have to use a diplexer and split the band in two. Whereas another option that we could pursue is an RF system on chip baseboard, where the ADC and the FPGA are actually integrated on a single chip, which reduces both the complexity and the total number of boards that we would need because of the fact that now we won't have separate ADC mezzanines connected to the digital signal processing device. So this new system requires significant effort to implement. So this is something that we're currently working on as well. So in terms of next steps, the first thing is obviously we'd like more dishes. We only have one 6-meter dish, and the second and third dish will help to quantify redundancy. We'd also like to see what our beam looks like in comparison to simulations, verify the on-sky system temperature performance, understand things like how does our gain change of temperature throughout the year. So things like environmental stability like this and how snow buildup might affect the system. We'd also like to investigate, can we minimize the losses using fiber cables? So this is RF over fiber. And as I mentioned in the previous slide, we're also trying to explore the optimal digitization. So we're exploring things like different hardware and software options, like the RFSoC, to see how we can robustly and economically recover the full band. So to just summarize everything I just talked about today, the CORD experiment is a next generation radio telescope that is going to observe across the 300, excuse me?
2 minutes left.
Okay, thanks. It's going to observe across a 300 to 1500 megahertz bandwidth. It's going to have 3 times the bandwidth coverage, twice the collecting area, and root 2 lower noise compared to CHIME. And we have a key focus on things like systematic control and redundancy. And we're achieving these goals with all these different technologies that I outlined today, where we've seen that the dish is sub-millimeter compared to a parabola, and we can see this across multiple dishes. We find that the reflection coefficient is less than around -10 dB for the feed, as well as a 50% aperture efficiency, which is difficult to maintain across a wide bandwidth. And the LNA has a nominal noise temperature of around 10 to 20 Kelvin. And since this is the dominant source of noise within the system, it's really important to keep this low. And we're also exploring things like different ways to digitize the signal and compute the channelization and everything that's related to anything digital that you can think of that was necessary for a radio cosmology experiment. And with that, I think I have just a minute left, but I have some bonus slides that I would like to show. So these are also, Cynthia mentioned that we have the 2 technologies for measuring the dishes, one being the laser tracker and the second being the photogrammetry. And we can see, as she also mentioned before, that the photogrammetry is a little less precise than the laser tracker measurement, but it's good to see that we're still agreeing within the sub-millimeter level with the RMS from the laser tracker and the photogrammetry measurements. Right, and with that, I'll stop there and take questions. Thank you very much.
Thanks, Ian. Do we have any questions? There is a question. Have you thought of using machine learning directly on FPGAs?
Huh. That is something that we haven't really thought of. And it's also something that's not entirely necessary because of the fact that anything machine learning you'd want to do offline. So the idea of the FPGAs is that basically the high data rate is enormous. It's something like terabits per second on the so first say CHIME, and we'd expect something similar for CORD too. So doing any sort of machine learning would be extremely difficult, and I don't know if FPGAs can even do that. But yeah, the FPGA isn't really at the point where we'd want to do any sort of machine learning because the FPGA, its primary focus is to, if we go down, say, for example, the RFSoC path, we want to digitize the signal, compute the FFT, get all the frequency channels. And if we're operating with D3A6, where we only have one ICE board, we're also computing the correlation there. So it's already asking a lot of the FPGA. So that's not really somewhere where we would be applying machine learning.
Thank you.
Oh, okay, I see. She's commenting that apparently they can use FPGAs to machine learn. That's pretty cool. I didn't know that. But again, for our purpose, I don't think that would be something that we would be looking into.
Okay, so if there are no other questions, so let's move the discussion to Slack channel and thank Ian again. So next speaker is Joelle-Marie from McGill University, who will talk about developments on a new low noise amplifier and antenna for albatross.
Hi, can you hear me?
Yes.
All right, great. So, hello, I'm Joelle, and I'm an undergrad at McGill University. And today I will be giving an overview of the albatross experiment And I will also be talking about some of the work that I've been doing in developing a new antenna and low noise amplifier for the experiment. So to start with an overview of Albatross, Albatross stands for the array of long baseline antennas for taking radio observations from the sub-Antarctic or 79th parallel. And this very long name is because there are two nominal locations for Albatross. One is on Marion Island, which is in the sub-Antarctic off of the coast of South Africa. And the other is in the McGill Arctic Research Station. And also recently, because of the pandemic, since we haven't been able to go to these locations, we've been using the Wapishka Station in northern Quebec as a site to test some things. And the goal of Albatross is to provide high resolution, full sky maps of the radio sky below 30 megahertz. And in order to access these frequencies, we need a couple of things. Firstly, we need really long baselines to achieve high resolution at these ultra long wavelengths. And on the bottom left, I'm showing a map of Marion Island, and the pins that have been dropped there are the planned antenna locations. And in this picture, you can see that the longest baselines are about 20 kilometers. Another feature of Albatross is that the planned antenna locations, deployment locations, sorry, are extremely remote, which is really important for dealing with RFI, and something that's especially important for the frequencies that we are interested in are locations with good ionospheric conditions. And so I will later on talk a little bit about the challenges that having long baselines and remote locations pose, but first I want to talk about the science goals of Albatross. And although the local radio sky, so the emissions from our own galaxy and nearby galaxies, are very interesting in their own right, the motivation behind choosing this frequency range for Albatross is that these frequencies correspond to the redshifted 21 centimeter line from the cosmic dark ages. And the ultimate goal of Albatross would be to map fluctuations in the 21 centimeter brightness temperature field from the dark ages, but there's a lot of work that needs to be done before we get there. And one important first step is to understand foregrounds, which are orders of magnitude brighter than the 21 centimeter signal. And so how well do we currently understand foregrounds? And as a starting point, we can look at the maps that were used to develop the global sky model, or GSM. And here on the right, what I'm showing you is the maps below 40 megahertz that were used in the GSM. And I've also added a 35 megahertz map from the LWA survey, which was done after the GSM. And on the left, what I've done is I've plotted the frequencies that correspond to each of these maps, which are represented as the colored bands, with the global 21 centimeter signal in gray, just for reference. And in the legend, I've also included the resolutions of each survey. And what I hope that this slide illustrates is that the data at these low frequencies is, number one, very sparse, and number two, low in resolution. And since the 21 centimeter signal is so much dimmer than foreground contaminants, we really have to do a better job at understanding foregrounds before we do cosmology at high redshifts with the 21 centimeter signal. And below 30 megahertz, in particular, the frequency coverage, as well as the quality of the existing maps, leaves a lot of room for improvement. And so that's where Albatross comes in. Here in light gray, I've outlined the target frequencies for Albatross, which range from 1 to 30 megahertz. And with the planned antenna locations, Albatross is going to achieve arc minute resolution. And here on the right, I'm showing the synthesized beam at 5 megahertz for those planned antenna locations that I showed a couple of slides back. And now what I'll do is that I'll give you a tour of the Albatross systems, going through this block diagram by sort of tracing the signal path. We start on the left with the antenna, which is connected to the front end electronics that consist in part of a low noise amplifier. And then moving on to the back end, we have a bandpass filter from 1.2 to 140 megahertz, a second stage of amplification, and then this filtered and amplified signal go onto the ADCs in the snapboard, and an FPGA that, among other things, saves baseband data to hard drives. And one of the challenges in working with very long baselines in remote locations is the difficulty in accessing the system physically. Because of this, each antenna station has to function completely autonomously. And one challenge in this autonomous operation is power. And our solution for this is to have a hybrid solar power and methanol fuel cell system which will keep our batteries charged. Another challenge is that since the baselines are in the orders of tens of kilometers, it's really not feasible to run cables between all of them to do direct correlation. And so with the help of a USB multiplexer, we will cycle through hard drive bank and save data directly to the hard drives for offline correlation. And so now to look at each of these individual pieces in a little bit more detail, here on the left is a CAD model of the box full of hard drives and the multiplexer boards. And on the right, you can see me with the army of multiplexer boards that I built last summer. And the idea is that an Albatross antenna station will be saving 1 bit of baseband data for about a year at a time. And to save all of these data, we are sending 16 8 terabyte hard drives to each antenna, and the multiplexer boards handle the switching between them. And now to look at the power systems, here's a picture on the left of the hybrid solar and methanol generator. You can see the solar panels in the back facing away from us. And they're supported by this big steel structure that also serves as a sort of chair for that gray box to sit on top of. And below the gray box, those white tanks are full of methanol. We have 480 liters of methanol, which should be enough to get us through the Arctic winter, which is 6 months of total darkness. And on the right, you can see John Sievers talking to the Raspberry Pi, which lives inside of that gray box you see there. That has the snap board, FPGA, and all of our backend electronics. You can also see the box that you saw the CAD model for in the previous slide with the hard drives and the multiplexer boards and our batteries that are being charged by the hybrid solar and methanol system. And so now, in the last couple of slides, I'll talk about the antenna and front-end electronics that we've been developing. And to motivate the need for this new front end, here is a waterfall plot on the left of the 2 antenna Pathfinder that was deployed on Marion Island a couple of years ago. And what we're seeing here above 15 megahertz is what we want to see for one baseline, which is fringes in the sky. But below 10 or so megahertz, we see a very sharp drop off in response. We don't see these fringes anymore. And the reasoning behind this is that we have been using the LWA antenna and front end for the first engineering runs of the experiment, and they have really been invaluable in testing all of the logistical aspects of the system because they're extremely well documented, readily available off the shelf, and easy to set up. However, they are not optimized for the lowest frequencies that Albatross is targeting. And here on the right, what I'm showing is a plot from Tristan Menard's master's thesis, which shows in solid blue the gain of the LWA antenna and in dashed blue the realized gain. And we've attributed this same sharp drop-off in response at low frequencies that you see in the waterfall plot to a large impedance mismatch between the front end and the antenna at these low frequencies. And so what we've been doing is developing a new front end board and antenna. And what I'm showing you here on the left is the basic architecture that we have chosen for the low noise amplifier, which is a 3 op-amp instrumentation amplifier. And part of the reasoning for choosing this architecture is that it is a differential amplifier. And we can also choose each op-amp very specifically to suit our low noise and frequency response requirements better than something that we could get off the shelf. And the antenna that we're developing, which you can see in the picture on the right, and it's also the title slide, is an inverted V dipole. And one nice thing about this kind of antenna is that it is very cheap. It's just a pole and some wire, and it's really easily scalable. So we can pretty trivially change the thickness of the wire or the length of the wire, the height of the antenna. And so it's really easy to tweak for prototyping. And since the last summer, we have built and tested the first version of our custom amplifier, as well as started on new revision, where we're aiming to have better control over the noise properties. And so here on the left, I'm showing the spectrum of the latest revision on the top panel, featuring a mysterious source of RFI in our lab that we haven't been able to track down yet. And on the top right panel is the S21, or the gain of the board. And then finally in the bottom is the noise spectrum, which is a combination of the 2 top plots. And a couple of things to note here is the relatively flat frequency response in the S21. Our previous revision did have a bit of a flatter spectrum, but we have changed a lot of the parts, and we just started working on this new revision this year. So there's still the possibility to make this response even flatter. And we also have decently good noise properties. So at the lowest frequencies, we're at about 3 nanovolts per root hertz, which is pretty good noise value. And although we haven't gotten this latest revision of the board on the sky yet, last summer when we were up at Wapishka, we were also able to test the first revision of our board on an LWA antenna. And this plot here on the right is comparing our front end on the LWA antenna and the LWA front end on the LWA antenna. And what we see here is pretty promising because we're seeing a pretty flat response at the frequencies that LWA drops off. And we also see shortwave radiation rearing its ugly head, even at the very quiet Wapishka site. And so just to summarize, now that the pandemic is hopefully calming down a little bit, we're going to go ahead with Albatross deployment to the target sites. In the coming months, we will be sending a lot of equipment down to Marion Island, as well as go up to the Arctic to install the first year-long Albatross station there. We also hope to be able to get our new antenna and front end on the sky to see what our sensitivity at these lowest frequencies looks like, and hopefully keep making progress toward getting the best maps of a low frequency sky yet. And with that, I'll end and thank you all for listening, and I'll take some questions now.
Thank you. Do we have any questions? I can ask one. So have you considered the ionospheric qualities, or have you ever like studied about it, that because low at these frequencies, ionosphere is expected to be extremely erratic? So
yes.
have you ever,
yes. So that's a great point. And so just for context, this shortwave radiation that you see here, that's all because of the ionosphere bouncing around that radiation, right? And so it looks pretty bad. I mean, the rest of the spectrum is super clean, except for a little bit of FM peaking up at the higher frequencies. And although I don't have a plot for that, you can look at Chang et al. 2020 paper, where they did do a little bit of predictions about the ionosphere in Marion Island. I don't think we have done that yet for the Mars location, but yes, Marion Island is expected to have better ionospheric conditions than a lot of other places. So that's super important in having less of this interference from shortwave radiation below 10 or so megahertz. Yeah.
Okay, there is a question on Slack. What clock setup are you using to sync baseband data offline?
What, sorry?
There is a question on Slack. What clock setup are you using to sync baseband data offline?
Yeah, oh, I didn't include that in my block diagram. I'm sorry, but we are using, right now, we're using a Leo Bodnar GPS, and I admit that's not my area of expertise, so I don't know that many of the specifications, but Leo Bodnar is the answer. Yes.
Okay, if there are no more questions, so let's thank Joelle-Marie again. And this was the last talk of the session. So thanks everyone for joining in, and we'll probably see you in the next session.
Thanks everyone. Thank you to the speaker and to Barrett for sharing. We'll resume with the next session in an hour. So at quarter to the next hour. Thank you so much.
Thank you.
Bye.
Bye.